Hey, this is the lesson 2-1 video, and I got a lot to cover. This video is going to be one of the longer ones, so I'm going to get right into it. Why don't you go to page 62 in your book? We're starting chapter 2 today, and this chapter is called Properties of Real Numbers, and we're going to start off with a section 2-1 called Using Integers and Rational Numbers. There's a lot of vocabulary in this section, and I just want to get right into it, all right? The first term that we need to be familiar with is what a whole number is. And I know you've heard of that before. Let's make sure you understand what it is. Whole numbers are positive numbers or zero, and these numbers have no mixed numbers or decimal places. So whole numbers would be numbers like 0, 1, 2, 3, 4, 5, and so on. Okay, you notice that none of these numbers have decimal places, and none of these numbers are mixed numbers. Remember, mixed numbers means things like 1 3/4. It's mixed. It has a whole number and a fraction mixed together. Okay? So, whole numbers are positive numbers or zero. They cannot be mixed numbers, and they cannot have decimal places. Integers. Integers are all these numbers. Integers are whole numbers, but they're also the opposites of the whole numbers. Okay, so any whole number is an integer, because any whole number, you can see any whole number would be part of the group of integers. Integers are whole numbers or their opposites. So integers also cannot have decimal places. Integers cannot be mixed numbers, but integers can be 0, 1, 2, 3, 4, just like whole numbers can. But the reason integers are a little different from whole numbers is they also include these negative numbers, like -1, -2, -3, and -4, so on. So that's the difference between an integer and a whole number. You also have the next group, and actually I should be erasing. Let me erase some of this here. Looks like I put some stuff up here, and I want to erase this out to make this a little bit clearer, easier to read. Okay, the next group is rational numbers. Okay, now any rational number is a number that can be written as a fraction. If you can write the number as a fraction, it's rational. Okay, so this sometimes causes people a little bit of confusion. Wait a minute, whole numbers, we can't have fractions in them, and what the heck is going on over here? Okay, well, I didn't say whole numbers couldn't be fractions. I said whole numbers can't be mixed, like 1 3/4. I can't have a whole number that's 1 3/4. That's a mix. It's a mixture of a whole number and a fraction. Okay? Any rational number is a number that can be written as a fraction. So if you look on page 64, there's a picture. It's a Venn diagram. I know you've used Venn diagrams before. And let me kind of draw what's going on in that picture and talk about it. First of all, we have whole, I'll just use WH, whole numbers. WN, I meant to say, whole numbers. Okay, in here are all the whole numbers. Now, around that are integers. Okay, and what this picture means is anything inside of this box is an integer. Now, if it's an integer, it's a whole number. Okay, time out. I just said that backwards. I meant to say if it's a whole number, it's an integer. Okay, so any of these numbers here would be integers. Integers, there are some integers that aren't whole numbers, like right here. Okay, numbers like -4, -3, -2, -1, those aren't whole numbers. Those would be the numbers right here that are not in the whole number circle, but they're integers. They're in this part. Okay. Then we have the next grouping, which is called rational numbers. Now, anything inside of this is a rational number. Now, rational numbers, remember, are anything we can write as a fraction. So integers and whole numbers, all of these are rational. So let's think, how can I write a whole number as a fraction? Because remember, rational number means you can write it as a fraction. Well, think about it. The number 2, I could definitely write that as a fraction. 2/1, it's a fraction. I can definitely write the integer -3 as a fraction. All I got to do is put -3/1. I just made it a fraction. Anytime you can write a number as a fraction, it's rational. Okay, so I hope I did a good job of explaining that. Whole numbers are any numbers that are 0 or positive, but they cannot have mixed numbers or decimal places. So whole numbers are 0, 1, 2, 3, 4, 5, and so on. Integers are whole numbers and their opposites. So you can see, if I, let me take my yellow marker here, you can see here, here's all the whole numbers, just like I had before up here. Okay? But it also includes the opposite of those, the negatives. But again, there are no mixed numbers or decimals in that grouping. And then rational numbers are any numbers that you can write as a fraction. Well, whole numbers and integers are all rational because every one of these can be written as a fraction by simply putting it over 1, like 7 over 1. I just made it into a fraction. Okay? Another thing we have to understand with whole numbers, integers, and rational numbers is that we have positive and negatives of those. And we'll be asked to graph those on a number line in this section, so I want to review a number line. So I use this sheet of graph paper just to make it easy for me to point out things on a number line, okay? And right now, for whatever reason, my pen isn't responding very well. So just give me a second. As you can see, it's waving around the page, so my computer must not have been keeping up with my Mobi here. Okay, so let me turn that off. Okay, so what I tried to emphasize here is my number line. I used graph paper just to make this neat, so you can disregard the y-axis, just pretend it's not there. All I'm interested in right now is the x-axis. Okay, so on a number line, there's a couple key areas we have to be aware of. Positive numbers are always to the right on my number line. 0 is always in the middle of the number line. 0 is where we separate the positive numbers from, of course, the negatives are over on the left. Now, one thing that kind of is a little, I don't know if it's a pet peeve or just a major mistake, and I've seen people do this before, and that's why I wanted to address it right now with you, okay? Up in the left-hand corner here in red, I have seen people on homework quizzes, tests, homework, write number lines in this way, and this is completely incorrect. You can never have a number line where the negatives are to the right and the positives are to the left. Okay, the positives are always right on a number line. It's like a thermometer. Think about temperature. The negatives are never on top of the positives. It's always positives are higher than negatives. You read a number line from left to right. The positives are always right. The negatives are always left. If you look at question 8 on page 67, this is one of the tasks you'll be asked to do, and I will always give you, when you come to class tomorrow, I will have pre-made number lines already made for you, so you're not going to have to get out a ruler and make them. I know that's a pain to do. So I have pre-made number lines made up for you. But if you look at question 8, the directions on page 67 are graph the number on a number line, or graph the numbers on a number line, and then tell which is greater. Well, they want me to graph -2 and -3. Okay, so first of all, when you graph, this is a key point, you need to draw the points actually on the number line. I have seen people graph, I'll do this in red, it's wrong. I've seen people do things like this. They'll put little, stars above the number line. That's not how we graph -2 and -3. I've seen people put dots above the number line. That's not how it's supposed to work. Okay? You are supposed to actually physically put those points on the line. That's actually graphing. Drawing a number line is not graphing. Putting these points here is the actual graphing of the points -2 and -3. And then they want me to tell which one is bigger. Well, -2 is greater than -3. The number farther on the right is always the greatest. Now, this little bit here concerns me. Every year I have people that come into my class and they have a misperception that this number here, let me circle it, is actually the bigger one. Okay? And I think they're thinking positive. I think they're so considering the positives, like 3 is definitely bigger than 2. Their whole life they've been used to saying, hey, 3 is bigger than 2. Well, now they look over here and they're like, okay, this is bigger. Well, no, it's not. -2 is farther right than -3. A real-life example would be like you owe your parents money. You borrowed money and you owe it. Okay? You owe it back. Are you in a better situation if you only owe $2, or are you in a better situation if you owe $3? Well, obviously, you're in a better situation if you owe only 2. You owe less money. That's the more positive of the situations. Okay? I would definitely rather only owe someone $2 than 3. -2 is definitely the greater amount. Okay? So you'll be asked to do that on homework in questions 5 to 13. Graph numbers on a number line and compare and tell which is bigger. Okay? I don't know why I did this here. I can probably get rid of that slide. It's the same as what we just talked about. Okay, the next thing you're going to be asked to do, since we've talked about whole numbers, integers, and rational numbers, go to page 68 and look at the group of problems from 14 to 22. And I'm going to read the directions with you, and then we'll do these. A couple of them. Tell whether each number in the list is a whole number, an integer, or a rational number. And then order them from least to greatest. Okay, so let's do that. Let's start off, and I wrote the numbers for number 17. We're going to do 17 together. I wrote these numbers out, and we're going to identify them. Okay, so let's start with -2/3. Is it whole? Is -2/3 of the group of numbers 0, 1, 2, 3, 4, 5? Well, no, it's not, obviously. It can't be whole. Wholes are only 0 or positives. No mixed numbers or decimals. This would be a decimal, 0.6 repeating. Okay, so can't have, that's not whole. It's certainly not an integer for the same reasons. However, it is a rational number. Remember, anything that can be written as a fraction is rational. Well, that's a fraction. Okay, let's do -0.6. Same thing. It's not whole. Okay, whole numbers can't have decimal places. Not whole, and whole numbers can't be negative either, so I know it's not whole. It can't be an integer. Integers can't have decimal places. This does. This definitely is rational. It's definitely a rational number because it can be written as a fraction. So let's speak this properly. I know most of us, and I'm just as guilty, I would always say -0.6. That's technically not the correct way to say it. Shouldn't we say this is -6/10? Well, think about what I just said. 6/10. Isn't that a fraction? This number is rational. It can be written as a fraction. Okay, -1. Is it whole? Well, nope, it's not whole because it's not 0 or positive. Negative numbers can't be whole. It is an integer, though. It's definitely an integer. It's definitely the opposite of a whole number. And it's definitely rational. I can write this number as a fraction. I can write it as -1/1. And then 1/3. Certainly not whole. Can't have 1/3. This is a decimal, 0.3 repeating. Can't have that, so it's not whole. So for the same reason, it's not an integer. This is definitely, however, rational. It's a fraction. Now I want to order these from least to greatest. Let's write these from least to greatest. So the least of these, the smallest is -1. That would be farthest left on the number line, followed by -2/3, followed by -0.6, and 1/3. I want to talk about this more because I always have people screwing these up. Okay, so let's just think about a number line real quick. And I tell you what I want to do to start. Let's just think of these three numbers as positives. 1, 2/3, and 0.6. Now, if I gave you these three as positives, I think most of you would be able to order these correctly. You'd say to me that 1 is certainly the biggest. You would tell me that 2/3, now 2/3 is 0.6 repeating. I'm very confident most of you would be fine with saying, hey, 0.6 repeating is definitely bigger than 0.6, so I'll put that here. And I tell you what, I'll just use yellow for 0.6. So I think most of you would be fine with saying, hey, this is the smallest, this one is in the middle, and +1's the biggest. Now here's the thing. Think about the opposite. Now we're talking the opposites of 1, 2/3, and 0.6. So if I keep on drawing my number line out here and put -1, wouldn't the opposite, wouldn't -1 be way over here? And wouldn't 0.6 Wouldn't 0.6, I did that in yellow, wouldn't 0.6 then be mirrored here? And negative point, or I should say negative 2/3 or negative 0.6 repeating, wouldn't that be here? Or something like that. I mean, maybe my drawing's a little off. But can you see that in this case, negative 0.6 is the farthest to the right. It's the biggest of the three. So that should be, that's not the smallest, that's the biggest of these three. Negative 2/3, that's in the middle, and negative 1 is certainly the smallest. Okay? Let's try another one. Let's go to 18. First of all, let's determine, are these whole, integer, rational? That's not whole because it has decimal places and it's negative. Certainly not an integer. It's got decimal places. This is definitely rational. It's definitely rational. Let's speak it properly. I mean, I know I would a lot of times say, just like you, negative 0.01. Isn't this 1/100th? Isn't that a fraction? 1/100? Negative 100? That's rational. Okay? Same thing for this. This is 1/10. 1/10 is not whole and it's not an integer, but it's definitely rational. It's a fraction. 0. Oh, that's whole. 0's whole. 0 is also an integer. 0 is also rational. It's all three. I can write 0 as a fraction. 0/1. There it is. It's a fraction. Negative 1/10. Certainly not whole because it's negative and it's a decimal. 1/10.1. Certainly not an integer for the same reasons. And it is rational, though, 1/10. Okay, so again, writing these in order. I'll do that here. Negative 1/10 is the smallest. Negative 100th is next. 0 would be next, and the biggest is a tenth. So again, my main concern is here, these two. Okay, think about both of these. Just think about the positives. So here's 0. If you think about the positives of these, 1/10 and 100, think about a candy bar. Would you rather have someone give you a tenth of your favorite candy bar or only 100? I'd rather have a tenth. That's more than 100th, right? So if we're talking positive numbers, 1/10 would maybe be here, where 1/100th would maybe be here. But if you take the opposite, these are the opposites of positive tenth and positive 100th. These are the opposites of that. Well, if I mirror those, negative 10th would be over here. Oop, I used the wrong color. I'm sorry. Negative 10th would be over here. Negative 100th would be over here. Well, can you see how negative 100th is actually farther right? It's the bigger of the two. Okay, so negative 100th is definitely bigger than negative 10th. Okay, go back to page number 66. Let's talk about absolute value. I know this is a review for most of you. This is something that would have been covered in 7th and 8th grade in your classes. Absolute value means distance a number is from 0. It's always a positive amount. Distance is always a positive. Think about if you've traveled up to the Mackinac Bridge. I think it's 220 miles roughly from here. If someone asked you how far was that trip, you'd tell them 220 miles. Now, you might tell them 220 miles north, but you'd still say 220 miles. At the same token, if you went to Detroit, Detroit's probably 80 miles away. If that same friend said, well, hey, how far was your trip to Detroit? You wouldn't suddenly say negative 80 miles because it's in the opposite direction of the Mackinac Bridge. You'd still say 80 miles. It doesn't matter what direction you went. It's always a positive amount. Absolute value is a distance. It's always positive. The symbol for absolute value, it looks like this. It looks like you'll have a number or a variable or something inside of these. I don't know what these are called. I don't want to say brackets, but these longer lines. This, and I'll just kind of underline it, this little thing here, these little bars mean absolute value. And when you see that, this is asking you what's the absolute value of negative 7. So I'm asking you, how far is this number away from 0? And the answer should be 7. Now, one thing we got to be careful of, and a common error I see people make. I'll ask people, what's the absolute value of positive 7? And sometimes this is the answer I'll get, and it's wrong, so I'm going to write it in red. I'll have people say, oh, well, the answer to that's negative 7. And then I'm taking my red marker, and I'm marking it. No, that's wrong. Okay? Think about it. How far is the number 7 away from 0? So here's my number line. Here's 0. Here's 7. How far is this number away from 0? It's a distance. How far? Distance is positive. It's not negative 7 away from 0. It's just 7 away from 0. Absolute value is always a positive number. In the homework, we're gonna have you do a few problems with that. If you go to page 68, I'll do a couple with you here. The group of problems from numbers 23 to 34, here are the directions. If you want to follow along with me, it says in black at the top of those problems, for the given value of A, find the opposite of A and the absolute value of A. So for problem 27, the number they give you for A, let me turn this layer on, the number they give you for A is 13.4. Okay, well, let's think about that. What is the opposite of 13.4? Well, opposite of 13.4 is negative 13.4. So for the given value of A, the opposite of A would equal negative 13.4. The opposite of 13.4. Now, the next thing, let's think about in this problem, what's the absolute value of A? In other words, I'll put a little question mark here, what's the absolute value of 13.4? Because A is 13.4. Well, how far is 13.4 away from 0? It's 13.4 away. It would be wrong for you to put negative 13.4 because we're talking distance. Absolute value is always a distance. Let's do another one. Let's look at 29. Question 29 says A is negative 6.1. So let me just write that off to the side here, maybe above. Okay, in number 29, A is negative 6.1. So the first thing I'm asked about is find the opposite of A. In other words, I'm asking you to find, I'm going to have you substitute in. Okay, we're going to take negative 6.1. A is negative 6.1. In other words, what I'm asking you to find is what's the opposite of negative 6.1? Well, what is the opposite of negative 6.1? Well, that's positive 6.1. Okay? And then next, what's the absolute value of A? That's the second thing they wanted us to find in question 29. Well, what is the absolute value of negative 6.1? In other words, how far is negative 6.1 away from 0? It's 6.1 away. I think a key point here that I want to emphasize, make sure we're all okay on, key point, okay? Opposite, the word opposite is not the same as absolute value. Those are not the same thing, okay? And a great example of that is question 27, okay? Because when A was 13.4, the opposite of A was negative 13.4, but the absolute value of A was still positive 13.4. You don't automatically get the same amount when you take the opposite of numbers and absolute value of numbers. So that's something you have to be able to differentiate. Okay, and finally, to finish up here, conditional statement. This is the last part of this video. We're on the bottom of page 66. What is a conditional statement? A conditional statement is something that has a hypothesis and a conclusion, and it's always written in if-then form. The hypothesis is the if part of the statement. Okay, so if one fact is true, that's the hypothesis. The conclusion is the result. It's the then part of the statement. So if one fact is true, then this is the result, is what a conditional statement is. Okay? Now, conditional statements can be true, but conditional statements can also be false. In this section, you will be given conditional statements. You will be asked to determine what part of the statement is the hypothesis and what part of it is the conclusion. And if it's true, you'll just say it's true. But if it's false, you will be asked to provide a counterexample. A counterexample means give me an example of why that is false. So I wanted to do a non-math example first, something that I thought would be easy for you to think through and not be confused with the mathematics of it. So here's a conditional statement. If you are a freshman at Frankenmuth High School, that's FHS, maybe I should write that a little more clearly. If you're a freshman at FHS, then you have first lunch. Okay, well, first of all, this statement has a hypothesis. The hypothesis, if you are a freshman at FHS, if it's a fact that you're a freshman at FHS, the conclusion then is that you have first lunch. Okay, is that a true statement? Think about that for a minute. You're a freshman. If you are a freshman here, do you have first lunch? And I think you're all probably coming to the same conclusion I am. That's true. Okay, oops. That's a true statement. Okay, that's definitely true. If you're a freshman, you have first lunch. Let's think about the converse of that statement. Let's say I reverse the statement around. Let's say that this was my conditional statement. If you have first lunch at FHS, there's my hypothesis in green. If you have first lunch at FHS, then you are a freshman. Let's see if that's true. If you have first lunch at FHS, then you are a freshman. Is that true? Some of you might be thinking, no, it's not true. Okay, well, can you give me an example of someone that has first lunch that's not a freshman? Okay, that's the counterexample. So I know this is false, and I could use the example, well, hey, I know sophomores in first lunch that are not freshmen. So this is not a true statement. Having first lunch at FHS does not automatically make you a freshman. Now, how does that work with some math statements? So if you go to page 68 and look at numbers 35 to 38, they will ask you to identify the hypothesis and the conclusion of these conditional statements. If they're true, you can write they're true. If they're false, we have to give a counterexample. So we'll do two of these together. In 35, here's the statement: if a number is a positive integer, then the number is a whole number. Well, if the number is a positive integer, that's my hypothesis. Okay, that's going to be my hypothesis. My conclusion is that the number is a whole number. Is that true? If I have a positive integer like 1, 2, 3, 4, 5, 6, 7, 8, 9, etc., is that a whole number? Are 1, 2, 3, 4, 5, 6, 7, 8 the whole numbers too? Well, sure they are. Okay, that's definitely true. Let's look at 36. Here's the conditional statement. If a number is negative, then its absolute value is negative. Okay, so the hypothesis in this statement was if the number is negative. Here's the conclusion. Then its absolute value is negative. Okay, let's think. Is that true? If I have a negative number, is the absolute value negative? Well, you're probably coming to the same thought as I am. That's not true. I can think of a negative number that when I take its absolute value, I don't get a negative result. Okay, here would be a counterexample. This is false. The absolute value of negative 6 is not negative 6, it's positive 6. Okay, so when you have a false conditional statement, you want to provide a counterexample. I'll underline mine in green. There's my counterexample. I just gave you an example that makes this statement false. I gave you a negative number whose absolute value is a positive amount. Okay, I know this video went on for a bit, and I want to stop it here, so I'm going to stop right now.